Yeah, it says it's started recording.
Awesome. Okay, and it's saying at the top, I can see that.
Yeah.
I can dismiss that. So, so over to you, Kasper. Thank you.
Yeah, thanks for having me, Phil. It's always good to present, especially with people I don't get to see that often. I've never been there, and I wish I would come next time, Phil, in person, but it might be a while. So good afternoon, good evening, I think. What time is it?
Just coming up 6 p.m.
Okay, yeah, good evening then. So my name is Kasper de Jonge. I'm a principal program manager on the Power BI team. I have been working on Power BI for almost 9 years. Initially in Redmond, working on analysis services, Power Pivot, and the tabular model. And now mostly together with Phil and our team, working with some of the largest customers who are using Power BI and trying to help them and also get feedback from them on how to improve the product. So with that, today we're going to talk about understanding the Power BI data model. So let me share my screen. And let me know when you can see.
Yep, it's good.
All right, great. Yeah, we already talked about this. Oh yeah, one thing that I do want to mention on the bottom, if you have any questions afterwards or later, I am pretty active on Twitter, so just ping me there and I'll answer questions there as well. So what we're going to talk about is understanding, I'm sorry. Oh yeah, okay, this is right. I have the wrong agenda from the wrong session, but it's okay. We're going to talk about today's understanding the Power BI data model. So what we're going to talk about is the basics. What is the model? We're going to understand relationships, and we're going to take a look at DAX. And all of these things together make the Power BI data model. And I'm going to quickly turn off the video because I'm not sure if the connection will be good enough. Okay, so everything in Power BI starts with the model, the basics. So the model itself was introduced in 2010 when we started introducing Power Pivot for Excel. We didn't just start from scratch. We built this upon 20 years of OLAP experience. It is designed for interactive analytics at the speed of thought, like being able to have pivot tables, to be able to drag in information, to be able to play with the data. Interactivity is key. It is built around an in-memory column store database called VertiPack. Sometimes I've heard people say that VertiPack is a bought solution, that someone at Microsoft bought VertiPack engine. It's not true. VertiPack was built from the ground up inside of Microsoft. So we built it ourselves. It contains a very powerful analytical formula language called DAX, as you're well aware of. We have Phil there, so he probably talks about DAX all the time, which I understand. So it contains a very powerful analytical language called DAX. In 2013, we started merging two things together. We first initially had Power Pivot for Excel, and we had the engine itself. When you were loading data, we would use our own tools to load in data into the engine, but it was not very powerful. In 2013, we had lots and lots of meetings, and we actually decided to merge Power Query back then into Excel. So then we had Power Query and Power Pivot engine, both sitting together in Excel. The engine itself is used not just inside of Power BI, it's actually used in lots of different places. It's used in Power BI, it's used in Excel, it's used in analysis service, and it's used in Azure analysis services. It's the same engine, it's the same development team building it, and it's built from a single place. So there's one source code that delivers all of these places. Right. A question that often comes up is, why do I need to have a separate model? And this is especially true for people who do not have a BI background or haven't been around a long time. They're usually like traditional developers. And they say, well, I just want to write a query and send it to the data source directly. Well, the reason is that business users want interactive analytics at the speed of thought. They want to be able to slice and dice, not write queries. They want to perform business calculations. I don't know if you ever tried to do a year-over-year growth with SQL. It's pretty hard. It's very expressive. It allows you to do KPIs, hierarchies, drill through, naming, translations. It supports high concurrency to support enterprise reporting, and you can apply security to the data. So the model brings all of these things together. So a understandable semantic layer that business users can understand. It makes sure that you can slice and dice. You can only relay things that make sense together. Add these business calculations, and of course, there's expressiveness, like these KPIs and these hierarchies. You don't have these things when you just have to write queries. So this is why we have a separate model. So what does the architecture look like? This is a very old picture, but it's still pretty relevant. What we see here on the bottom is all the data sources. When you load in data into the semantic model, into the engine, everything goes through Power Query and M. So you connect the data with Power Query and M, you do your transformations, then data gets loaded into the semantic model, into the data access layer. And this, now you're getting into two different flavors, either Vertipack, the in-memory column store database, or direct query, where data flows through. SQL queries get generated by our engine and sent through Power Query into the underlying database system. Of course, on top, after you've loaded in data, you can apply business logic and queries using DAX. And then you can define your actual model, your tables and your relationships using Tabular. Then when you have this semantic model created, on top of it, you have ability to connect it to third-party applications, of course, reporting services, Power BI, but also Excel. Now, this has been there for quite a while, and this is also the way that it works in Excel. This is also the way that it works in the Azure Analyst services. But if you get Power BI Desktop, you actually get three things bundled into one. You get the visualization engine, for those of you who've been around longer, previously Power View, the engine itself, and analysis services, and Power Query. So we actually took three different product groups, three different entities, and bundled them all together into Power BI Desktop. So this is what you get. This is the architecture it looks like under the covers. But if we are looking at understanding the data model, we have to understand kind of how the flow works. So the first thing that we're going to take a look at is how does loading of data into this data model work? Well, the most important thing is it gets loaded through Power Query. The most amazing thing about Power Query is it allows you to have connectivity in a similar way to about 87 plus data sources. I think we're now about like 100. This slide has been pretty old, but it's a consistent experience that makes it important. So it's a connectivity to a wide range of data sources of various types, shapes, and sizes. It's highly interactive and intuitive experience for rapid and interactive construction of any data source in any size. It allows you to connect to very large data source because it only uses a subset of data to work over. I think the most important one is this consistency of experience. Whether you connect to a JSON file or you connect to a SQL DW or Oracle, it always looks the same. Power Query always looks the same, and you can do the same things with it. So there's no difference into the actions that you can take. The biggest difference that you will see, though, is, and we'll talk more a bit about this later, the biggest thing that you will see is that performance does change. So even though you can connect to all these data sources in several manners, the only thing that changes is the performance. And finally, you can join across different data sources. So you can combine this data from a text file sitting on your desktop to an SQL Azure database and create a single one. So you're probably all familiar with this one. This is the query editor. So what actually happens in this query editor? First of all, when you load in data, you apply transformations on top. Then you get a formula bar, and the formula bar allows you to create the formulas itself, right? So whenever you do a transformation, it results in a formula. Every formula, every step you take results into query steps. So you see a list of steps in the end. That is what's getting generated. The evaluation flows from the one step to the next. So the results of a previous step are used in the next step. So in this case here as well, if you go back, you see the first one is a source, so you import data. Then we say which table we want. Then we have a step called filtered rows, saying, okay, on the table that we have, I want to filter down the rows. And then I want to expand the table. And then, so every previous step is being used in the next step. So the step is stored into a variable, it can be reused later on. M has lazy evaluation though. So if you are loading data into a step and you don't use it, then the value is ignored. So what does that mean? So let's say, for example, here I have a very simple M expression. And again, I probably wouldn't have typed this. I probably would have used the UI to generate this. But this one allows us to connect to a website. It gets a table from the website and then renames the columns from that table into a rank and 2013, and then results into a table. And again, this is important. Every query steps that you make and take, in the end, results into a table. Same thing here. Here, what I'm doing is I'm connecting to AdventureWorks. I am loading in 3 different tables: dimcat, dimsubcat, and dimcustomer, and then I join them all together. The biggest difference here is, of course, you see we're joining the dim subcategory and dim category table using an inner join, but we're not using the dim customer table. Even if you would have this expression in your data source or in your M expressions, the dim customer table would never be loaded because, again, it's using lazy evaluation. But again, the result is a table. That's important. When you connect to and import data into Power BI desktop using Power Query, every step that you take that results in a table will be then eventually loaded into the next step where we're going to next as a table into the model. One other very important topic is in here, and this is key for Power Query as well, is something called query folding. So query folding allows us to, when you connect to data and you do all these steps that we saw before, what Power Query tries to do is it tries to push all these steps down into the data source so it doesn't have to do the steps himself. So let's take a quick example. So again, here I have this expression, and again, I didn't type this expression, I used Power Query to do so. So I loaded in the product table, I removed some data, I renamed some data, and I filtered down the data. So I did all these things. If you now have to think about what do we have to do here? Traditionally, if we wouldn't have correct query folding, this would mean that we would load in the entire dim product table into our in-memory engine, either on your Power BI desktop, on the Power BI service, on your Power BI premium capacity, on your Azure Analysis services. You have to load in the entire dim product table and then do all these transformations on top. All of these cost resources. They cost CPU time on your desktop, on your Power BI premium capacity, and things like this. But if you're using a smart data source, something like SQL or Oracle or something that is understandable, that can understand transformations, Power Query is smart enough to transform this into something else. So instead of doing all the work itself, it actually generates a SQL query that sends a query like this to the data source. So again, it's doing all the same transformations that we've applied using the UI, but instead of Power BI doing all the work, we let the SQL Server database do all the work. Again, this is much more optimal because usually the SQL Server database is pretty good at this. And second of all, we don't have to do all the work inside of Power BI. So then it generates a query like select product key, English product name. So you can see the rename operation. We do the filtering, the table that we've selected, and that's something that is called query folding. You can actually see if something is doing query folding when you're using Power Query. If you go to the last step in your Power BI table, you can actually do right mouse click and see native query. That will actually show you the query that's getting sent to the data source. If that is grayed out or doesn't work, then we're not able to do query folding. Unfortunately, it's a little bit of a hazy area that it's hard for us to predict when something can be query folded or not. So there's no good. Actually, I saw Twitter a thread on Twitter on this one last night actually, that people are asking, okay, when does exactly something gets query folded or not? But it's really hard to do because this is dynamically generated. It is based on lots of different things. For example, Power BI tries to detect if your data source supports it. Second of all, it depends on the M script that you have, all the transformations that you've done. So there's lots of variables that go into whether or not query folding is being supported. But if you do something like this and you use like SQL Server, then chances are really, really high that query folding is being applied. And again, this is important when you start thinking about performance, for example, or you start thinking about, okay, I have a premium capacity and I want to load as much as I can on that premium capacity. Well, if you use this, then less is needed of your premium capacity. You can put more stuff on it during refresh time. So that's query folding. So the question that also comes up sometimes, and this is less these days than it was when we just started this, is where do I manipulate data? So a lot of people, and especially like I was in the same boat because I was very heavily DAX and things like this. I would use DAX to create calculated columns. I would use DAX to do all kinds of things to manipulate data. But thanks to this query folding that we just saw, I actually made me want to do more in Power Query than in the Power BI data model using DAX. So if you need to do any manipulation of data, then use Power Query whenever possible, because it saves you storage space, because if you use DAX to manipulate data, then data has to be loaded into the model. With Power Query, you don't have to do this. So data actually gets stored in the underlying data source, and only data gets loaded that is needed. The benefits, of course, there's easy UI. There's a very rich language. You can do lots of different things with it. And of course, data folding pushes down the data to the data source. So there's no load on Power BI, which also is really good. Any questions on this before I go to the next step?
Actually, I have a question regarding the slide with SQL query. You sure? So when you told that when you run the script, is it executing the SQL query automatically, or you should specify in advanced settings the SQL query parameters to the database?
So what happens here is that this query gets generated based on the M expression that you have there. So no one typed in any SQL queries here. The M engine generated this query. So if you add new things or you do something else in your M script or in your steps, then the query will change as well. So no one typed this in. It automatically gets generated. And when you refresh the data, when you load the data, that's when this query is being generated. And that's also when it's being run.
So in other words, if I just specify the parameters to run the SQL query, it wouldn't improve the performance because Power Query is generating SQL query automatically.
Potentially it could improve performance if you know how to write the exact same query that is how your database is being tuned at. It could potentially improve performance, but I mean, it's not a general statement that writing a SQL query would be better, more improvement than what Power Query already does.
Okay, thanks.
Yep. Anyone else before we continue?
Yeah, I had a question. So, in the position where a query could be written in DAX or Power Query, but the Power Query wouldn't necessarily result in a SQL query being created, would you tend towards Power Query or DAX? And if so, why?
So I would. So a query meaning, and then that would mean like adding a calculated column or creating a new table.
So you have the option of doing either in DAX or M.
So I would. I mean, it depends a little bit, but in general, I would say use M. And the reason why I'm saying this is because when you're using DAX, and we'll get to this more in a second. When using DAX, the source data that you're using for your calculation has to be already in the model. If you use M, then your source data, the one that you're using to do your transformation on top, actually does not have to be loaded into the model. So only the result, the output, will be loaded into the model, which saves performance, like load time, but also saves memory, because you don't have to use both columns, or maybe even 3 columns or 4. So the source data can actually be used in Power Query then you can delete those columns and it still would work. And you don't have to load them into the model.
Right. Yeah. I follow you. Thank you.
But the other area is like sometimes Power Query, like the only reason really why we use DAX and for calculating the columns and things like this, if you do calculations across tables, because M doesn't, well, it does, but like that's very complicated and expensive. If you want to do, like, for example, if you have a products table and you want to see the sales of each product, if the sales of each product is larger than something, you want to add an annotation that you want to use in your slicer or something, and the sales are in the fact table, then I would use DAX, because DAX can easily traverse across tables, while Power Query and M cannot.
Yeah, great. That's really good. That's kind of where I was at with my own position. And I found that when you were going across tables, I would use DAX, and when you were working within tables, M. So thank you.
Yep, sure. All right. So as I said earlier, when we're at the last part of what you've done in Power Query and M, the result would be a table, and that table now gets loaded into the model. So in our engine, data is either stored in memory, in Vertipack, stored at the data source level, or stored at the data source level using Dara Query. In-memory is fast and interactive, built for analytics and expressive with DAX. Dara Query is always up to date, relies on data source performance, and it's not as expressive. Again, writing a year-over-year calculation in Dara Query is very interesting. A lot of people want to use Dara Query all the time because they don't want to load data, they don't want to do anything, but our state is just the opposite, actually. From the outset, use the Vertipack engine unless you're really convinced Dara Query is the right way to go. And again, I'll touch more on Dara Query versus in-memory later on. So what are some of the design principles that we have for Vertipack? Of course, performance, performance, performance. Another interesting one for those of you who've been around longer and have worked with multidimensional models, and also for those of you who work with in-memory engine from SQL Server, which actually is the same engine. So they took our Vertipack engine and shoved it into SQL Server and made some changes. But in general, it's the same engine, but they have different design principles. Because as you can imagine, query performance is more important than processing performance. Is ideal for us because you load data into the model and then you start analyzing. And we want to make sure this analyzing is fast. Processing is okay, we're okay, but waiting a bit longer. But if you use the column store database for SQL Server, then this is not the case because processing means inserting and deleting and updating rows in SQL Server needs to be fast, because otherwise, what's the point of SQL Server? So for them, actually processing performance is more important than query performance. So they've changed some of these characteristics of our engine. That's why it behaves a bit different. And that's another big difference, which I'll touch upon in a second. Again, number 3 is when you have been around with multidimensional for a while, then you know whenever you make changes into multidimensional models, you have to reprocess the entire thing and update and things like this. In the tabular model or in the database, in the Power BI data sets, we can just add a calculated column, you can just add measures, you can add relationships, you don't have to reload anything. It just works. So that's an important design principle. So what does it mean and how does it work when you store all data in memory? Well, again, all data is loaded in memory. And we have a column-based compression that enables, again, it's an old slide, so I should probably update it to billions of rows by now. But back then in 2010, this used to be millions of rows. But the way that it works is that imagine we have a table like this. We have IDs, we have years, we have months, we have a salesperson, and we have numbers. What happens is when this data gets loaded into the analysis services engine, the analysis services engine is going to look at all that data and it's going to try to find duplicates. Whenever it finds a duplicate, so in this case, for example, the year, it loads in the data, it looks at the first value and it sees, okay, it's a value called 2010. I'm going to store the value 2010 somewhere in a different spot. And I'm going to get a pointer to that value and store that into my database. And I'm going to do the same for everything else. So next, the next row is again 2010. I'm going to see if that data of that value already exists. If it does, I'm just going to store the pointer to that value instead of actually storing the entire value. And this is we're going to do for the entire table. So instead of actually storing the values, we're going to store pointers to those values, which allows us to do compression, really big optimized compression. The same thing goes for like months. In this case, we have 2 months, and I'm only going to store two different values, very small pointers instead of the entire string. Of course, things fall apart when we start doing IDs and numbers, because those cannot be compressed well because they're very unique. So also we have two different compression algorithms. I won't go into too much details there, but there's different compression algorithms for both. This is also why we say often, if you load in like fact table or something like this, stay clear of things like IDs in the fact table, because it cannot be compressed well. It's going to eat up a lot of space, and oftentimes you don't need it. So this is how compression works in a nutshell. So how does this data get loaded? So first we have a table, and we load in data with three columns from a database system. What it's doing first, it's again, as I told you before, it's storing data in segments and dictionaries. So the value gets stored in the dictionary, and the column segments are the pointers to the dictionary, to values in the dictionary. And it does this per, I believe, Phil, do you know, 8 million rows or something in Tabular?
You can fiddle with it, but yeah, Power BI is 8 million.
Yeah, 8 per 8 million rows, and then it segments them, so it starts to do it again. This is why some people like Marco and Alberto say, if you order your results, if you order your table when you import data, you might get a better compression, because we start looking into this dictionary every 8 million rows. But again, this is detailed. Calculated columns are actually stored like a regular column. So the expression is getting run, and we'll talk more about that expression in a second. The expression is getting run, and then data is getting stored in the same way to dictionaries and column segments. Then the other thing we're generating under the covers, and this is something you don't see, but we also generate hierarchies under the covers. It provides quicker access for querying. This is mostly used for two reasons. One, if you want to do sort by auto column, and second, if you use MDX queries. So if you use Excel against Power BI or an analysis service dataset, then we need those hierarchies. If you do not need them, you can actually turn them off. There's an option to turn it off, because again, when we load the data, this all has to be done. So we look at hierarchies, we see what the ordering is of the attributes and things like this. So it all takes time. You can actually turn this off. You cannot turn it off in Power BI yet, but maybe at one point we will. In analysis service, you definitely can.
Can you give us a definition of a hierarchy? I mean, are we talking just like dates, the classic one?
It's under the covers. This is something you cannot see. It's not a user hierarchy. It's a hierarchy that actually stores into our engine.
What is a hierarchy in plain English?
So I was just getting to that. The hierarchy here is the ordering of the values in that table. So what's the order? Like A, B, C, D, E. And so we order the values inside of the table, so that actually in MDX you need to have the ordering to be used, so you can do all the MDX calculations. Again, it's an implementation detail mostly, if you ask me.
Okay.
But it needs to be there, otherwise there will not be. You cannot use MDX. So if you turn off the hierarchy creation inside of with that property that I talked about, then that column will disappear in an Excel pivot table. So when you connect then to that table from Excel, you will not even be able to see that column, because we can't use it. That's okay, because usually you do this on keys. You turn off the attributes creation on keys, and you turn off the attributes creation on like sales amount, on values that you use in your aggregations, because we can still do some of sales amount. We just cannot use them on rows and on columns, and that's what it's being used for, to be able to determine the order. In DAX, we do not use this at all. In DAX, you have to actually order yourself. So if you write a DAX expression, we always, like the engine or the visualization stack of Power BI, actually generates a query that says order, and then the formula engine actually does the ordering, where before it was part of the model. All right. So the second thing, so we do the same thing when you have table 2. Now, the other big difference between our engine and, for example, the in-memory column store database from SQL Server is that we also store relationships. So when you create a relationship between 2 tables, we actually create a dictionary in the model that actually says, okay, well, data from this table you can find for this row here. So we can do quick access. And the reason why we do this is because 9 out of 10 times, the reason why we want to have model and data into 2 different places is we want to do slice and dice. Dimensions by facts, like sum of sales amount by products. And by the sheer fact of having these relationships, we can do these lookups very, 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 very fast. SQL Server doesn't have this, and again, their design principles are a bit different, so they don't do this, and this also helps with their processing performance. Because again, that table result set that we had in M gets loaded into the model, and we have to do all these steps when we do processing. We load the table, we store them in the dictionaries, we create the calculated columns, we create the hierarchies, we can create the relationships, and then finally we're done and we can start accessing the data with DAX. Yeah, partitioning is also another part you can do. One thing that I do want to mention is that partitioning in SQL Server, for example, can help with performance. Partitioning doesn't do anything for performance in DAX. Only it is used for loading speed and loading performance. Right. The other important topic and thing that I want to talk about is the data is always queryable. That's also interesting. So when you load in data, it remains queryable. On load, when you start loading the data, because like, for example, we don't want you to have your data set in Power BI and your CTO is happily looking at the numbers, and then all of a sudden we start processing the data because it's like, it's the time of the data we do processing. All of a sudden his reports are no longer available. We don't want that. So what we do is when we load data into the engine, we actually create a duplicate structure in memory. The new data gets loaded and the old data stays there to be queryable. When loading is finished, the 2 data sets get swapped. Now both are in memory at this moment, and then the old data gets removed. So what does this mean? It means that when you do processing, you have the same amount of, you need to duplicate amount of memory because we need to load the same data twice. And the old data gets removed and the data gets moved back again. So when you're loading data in memory, you actually need a lot of data. The important thing is that you can tune this with using partitioning. Because when you do partitioning, you can only load parts of the data. It simplifies this. And also incremental refresh that we have in Power BI now. This simplifies this, and this allows you to load in only parts of the data that you need. So for example, only the last week. Power BI today, before we had incremental refresh, you always had to load in everything, which means a lot of memory usage. If you just use Power BI Pro and you use the shared capacity, it doesn't really matter. If you use premium capacity, then you might want to think about tuning this. Because again, the more memory you save, the more you can load up onto it. All right. To sum it all up, loading data. First data gets loaded through the Power Query engine. Power Query passes to the AS engine. There's also a little tiny implementation. What we try to do is we try to stream it. So we're not going to wait until all data is loaded into the Power Query engine. We're actually going to start streaming as soon as we can to the AS engine. So when the first rows hit, we already start to push it into the AS engine. This is not always possible. And again, this is one of those interesting implementation details that is not well documented. Again, to stay queryable, a copy of the data gets created in memory. And after all the data is loaded, all data gets removed and new data gets replaced. And capacity/memory varies significantly based on what you're doing. So if you have lots of calculated tables, calculated columns, if you have high cardinality columns, if you have lots of big strings, all of these change your characteristics of loading the data. There's lots of tools out there like DAX Studio, you can figure it out. Vertipack Analyzer actually allows you to look into the storage of how the data is getting stored, how many unique rows, what kinds of compression is being used, so you can start tuning this. But this really only gets interesting when you want to either spend time to save money somewhere, like either in the processing or either in your premium capacity or in your Azure analysis services. Then these things really make a difference. Otherwise, I wouldn't bother about it too much. If you just use the basic principles, like do most of the work inside a Power Query, create a dimensional model, then life should be good. Any questions on this? No? Okay, then I'm going to go continue. So after we've loaded in the data into the model, now the most important part comes. Creating relationships. Relationships is where the magic happens. So what I have here is a very simple model. It has sales, it has customers, it has geography, it has products, subcategory, and category. Again, this is a snowflake, but shown a bit differently, but this is a snowflake diagram. So imagine we have something following like this, and this is a screenshot of a very old Power BI desktop. Before it was called Power BI Desktop, it's called Power BI Designer. Even the colors are different and things like this, but in the end, it works the same. So what I have here is a field list, and I've dragged in English country region name. The first thing that now actually happens is already did something special, because we dragged an English country region name, and we didn't get all the English country region names. We got a distinct list of all the English country region names. You immediately see it. So there's no Australia twice, it's only there once. Automatically, the engine did something. It created a distinct list of these English country region names. Now, the second thing that we're going to do is we're going to drag in sales amount. And this comes from the sales table. And automatically, something magically happened. I didn't have to write an inner join. I didn't have to write a group by. I didn't have to write a sum, which you would have to do in SQL. I just dragged and dropped. And now we have sales by country, and we have a grand total. All of this automatically happened. So in this case, for example, Canada has almost 2 million in sales. How does this work? Because if you understand how these relationships works, it will get easier for us to also understand how DAX works when we talk about this later. So what we have here is what happens is we're going to apply filters, and we're going to sum of sales amount on the rows that are left. Again, what does that mean? It's something that we call, oh, the colors are not great. What we call here is, this is what we call filter context. We'll get back to this. Just remember, what you see here is what we call filter context. Under the covers, so you don't have to understand this or see this. Under the covers, this is what's getting generated. A big query that is going to be sent to the query engine. You don't have to write it yourself. Power BI does this for you. Okay, so how does this work? What happened? So first of all, we need to understand how relationships flow. For those of you who are using Power Pivot, you will see we recognize these arrows. These arrows, we had lots and lots of discussions on internally what they should look like. These arrows look like an ER diagram, like traditional COP ER diagrams. This is what the arrows look like. This is confusing. At least that's what the result that we came up with in the end with Power BI. So we decided, okay, we're not going to use the COP diagram, ER diagram. We're going to show you in the Power BI diagram how data flows, how relationships flow. This is what the arrows will point to. So what we have is, because we're looking at this row for country name is Canada. This means that a filter of country name is Canada is being placed on the geography table. The geography table has 655 rows. This is getting filtered down by region name is Canada, which leaves us with 73 rows of the geography table. This is not the end, because what we need to go do is we need to get to the sales on the sales table. So this filter of country name is Canada is being pushed into the next table, because we need to go all the way to the sales table. Now, what it's going to do is going to filter the customer table to only show customers that are from the region name is Canada. So again, we have 18,000 customers, but in Canada, we only have 1,571 customers. Okay, so the table gets filtered down to 1,571. Now, because this is where we need to go to the internet sales table. Now the internet sales table is going to give us the sales for customers that live in the region Canada. It's going to go down from 60,000 rows to 7,620 rows. Now, this is the result set where the filters are being applied. Over the 7,620 rows, we're going to do the sum of sales amount. And this is the end of the line. It's not going to go anywhere further. These tables are not filtered. And this is going to get us to 1,977,844. So what happens is the filters getting applied for every row inside of this table. This is what is actually happening under the covers in our engine. Every row inside of this table, it is doing this filter operations, and it's doing the same from the grand total. The country row name is the only filter. So how does relationships works? Data always is filtered from the one to the many side. This is great when you have a nice traditional star schema, but unfortunately, we don't always have a nice star schema, or we want to use counting values in a dimension. What do we do then? So let's take a look at a scenario. For example, in each country, how many customers bought bikes? So what we did here is we had the same English country region name. We dragged an English category name, and we dragged in the count of customers from the customer table. And you see immediately something is wrong. It's not showing us the results that we want. It's showing us every region has every product category name, and it shows us all the count of customers themed for every region. It's not showing us by product category name. What's going on? Again, you see the same value again is repeated over and over again. We're doing the same thing. Remember, we're applying filters and we're counting the remaining customers. Now we have two filters, country name and category name. Because now the country name is there, we also have a filter on category name. And again, it's doing the same thing. Now the sales table is being filtered by country name is Canada and category name is bikes. If you would look at sum of sales, it would work. But this is not actually what we wanted to do, right? We wanted to have a count of customers. But as we saw earlier, this is where it stops. It only follows the relationships where the arrows are pointing in the direction, one to the many side. It does not go to the customer table. So the count of customers is only being filtered by the English country region name, not by the category name. It's not filtered by product category. So what do we do? Well, this is where bidirectional cross-filtering comes into play. So also known as many-to-many, maybe it's an interesting story to tell as well. There has been many discussions on the name many-to-many versus bidirectional cross-filtering versus all the other things. We've decided to not call it many-to-many because it is not really a many-to-many. If you ask SQL Server people what many-to-many is, you get different results than when you ask someone who's building multidimensional models. We didn't want to add more confusion. So what we tried to say is, okay, we're going to describe the functionality by saying it's bidirectional relationships. It changes the data flow. It is a very simple change. You just go into the data set here and you change the cross-filter direction to both. You press OK, but it has many implications. As soon as we turn on bidirectional relationship here, the arrow changes directions, and now the customer is filtered by both product and the category. Okay, so it has many implications. But it also means now that your customer table is always being filtered by the sales table. So maybe you want to see customers, a list of all your customers. Well, if you filter it by bikes somewhere in your report canvas, you will only see customers that have bought bikes. Some cases you want it, some cases you don't want it. It's cost performance, and it can also lead to confusing behavior. I won't go into too much details on bidirectional cross-filtering, but in general, the best practice is either turn on bidirectional cross-filtering on the relationship diagram, as I just showed you, really only when you are confident you want to do this. Alternatively, instead of putting it on the model, you can actually use it in a measure. So you can turn on bidirectional relationship in a measure. So in this case, for example, if you want to do count of customers, you can actually turn on the bidirectional cross-filter in your customer table, in your measure, and then bidirectional cross-filtering will only be used in this measure, not when someone is just dragging and dropping things in. Again, I won't go into too much detail. There's a whole white paper on this, bidirectional relationships white paper. It's on the Power BI help documentation website, and it goes into lots of details. In general, I would say bidirectional cross-filtering is great, but be careful when you use it. The final thing that I wanted to mention is a lot of cases where we used to use bidirectional cross-filtering is actually to get this behavior. So let's say you want to have a slicer, and you want to have a slicer in your report by customer, but you only want to have customers that actually have sales in your slicer. Not all the customers. Maybe you had a customer 20 years ago, it's still in your customer table, and it hasn't had sales in like 15 years. So you don't actually need this to filter on this anymore. People would use bidirectional cross-filtering to filter out that customer from the list. It will lead to all kinds of performance issues. These days, you can actually turn on measure filtering on a slicer. So you can actually, instead of using it bidirectional cross-filtering, you can say, okay, show me all the customers that actually have sales based on my sum of sales amount. That is much better performance-wise, and also you don't have to use bidirectional cross-filtering. So again,
when you create relationships in Power BI, how does it determine what kind of filtering behavior it's going to have? The reason I ask this is I created a relationship in Power BI. Normally I use Excel, but I did one in Power BI the other day, and it automatically gave me a many-to-many, and I was surprised that it did that.
So we'll get to many-to-many in a second.
Okay.
But so there's this makes things even more interesting. We now also have an actual many-to-many relationship. So what it does is, in general, when it looks at the cardinality of your data, when it can actually detect a one-to-many relationship, then it will create a one-to-many relationship. In your case, you probably have duplicate values. So you have like a city that's getting repeated twice in each side of your relationship. So actually,
I didn't. That's the weird thing. Because I could change it to one-to-many. If I had duplicates, it wouldn't let me change it from one-to-many, right?
Yeah, that's true.
All right, I'll show Phil.
Yes, you should, and maybe you should file a bug. But in general, what it does is tries to get a one-to-many relationship. The other reason why we have real many-to-many relationships, I'm not sure if that's the case, it's when you have composite models. Were you doing anything with direct query by any chance?
No.
Everything was loaded. Yeah, then show Phil, and then we can look into it. Because in general, what it does, it tries to generate a one-to-many relationship. Actually, in the past, we would automatically turn on bidirectional cross-filtering as well. That led to many problems, so we turn it off quickly. Now the basic is we do one-to-many relationships. We do many-to-many relationships, real many-to-many relationships, but only when you want to have join two tables that are not unique in either table. That's what you see here. You previously had to introduce another table containing just unique states, so you had to denormalize it, or had to normalize it. But there are interesting characteristics on this many-to-many because it doesn't allow you to do certain DAX expressions. But it's really useful when you do things like when you want to do composite models, which we'll talk about in a second. In general, we would generate one-to-many relationships. Yeah, so the behavior is, or maybe that's another interesting thing to mention as well. What we do here is we have, when you create one-to-many relationships in Power BI, what we do automatically is when you have sales that do not have values in your dimension table. Like, let's say you have sales for products that you do not have in your dimension table anymore. What we would do is we would automatically show the sales and show a blank value inside of the model. And the reason why we're doing this is because we do not want to lose numbers, sales, facts, because that could lead to very dangerous wrong results. When we have many-to-many, that doesn't work. Also, the interesting thing is when you use direct query, the reason why we generate outer joins in direct query is for the same behavior. We do not want for you to lose data and not being able to see there's fact data that does not have a dimension, like a city or a state or a date or a time. So we'll show a blank row. In direct query, you can actually tune this. You can say, okay, I'm actually confident that my data is correct. Turn on a function that is called, I'm not actually quite sure what.
The well-named one.
Sorry?
The well-named one.
Yeah, I'm not sure what it's called again, but you can on the relationship diagram, you can actually turn it on, and then we'll actually generate inner joins. When you use many-to-many relationships again, it is not possible to use the related function, and also the all function on the table will not remove filters. So that's interesting. Again, I would recommend you 99 out of 100 times, one-to-many relationships should be enough. So recap, relationships are the key to creating a great drag and drop experience. Data is always filtered from the one-to-many side, except when you're using bidirectional relationships where it flows both ways, and filter context, which you use to filter data. So make sure that in your model, try to use one-to-many as much as you can. Bidirectional relationships, I think Marco and Alberto call it like it's evil to use them or something like this. They really don't like it. I tend to be a bit more pragmatic. If you need it, use it. But at least be aware and make a conscious decision of when you start using it. And under the covers, whatever you're doing here is what's generating filter context. That brings us to the last, or almost last topic, called DAGs. Any questions on the previous part? No? Okay. So then we're going to see what you can actually use those relationships for. So again, DAGs is introduced as Power Pivot add-in for Excel. It's formulas for calculated columns, tables, and measures. It is actually the same syntax as Excel, including many Excel functions. When we designed the engine, when they created the engine the first time, they actually took a lot of the code from Excel that has these functions and copy and pasted them into our engine. That's why a lot of the functions look and feel the same. We actually took a lot of the Excel code base into our engine. But it has a lot of capabilities beyond Excel formulas. You can navigate relationships. You have dynamic calculation of measures, table valued functions, time intelligence, variables, queries. All these things are possible inside our formula engine that is not possible inside of Excel. You can use the model to your advantage. Every DAX expression is evaluated in a context called evaluation context. We just saw one version of it called filter context when we looked at that pivot table or that table that I showed you before. There are two different flavors of it. There is row context, which is being used when you do calculated columns or row level expressions. We'll talk more about this in a second. And filters inside of filter context. Initial context in a pivot table cell or in a visual. And then you can use the functions like filters, etc. What does that mean? So let's take a look at a quick example. So initially, when I just drag in from the invoice table, sum of revenue, it automatically gives us the grand total, sum. It takes all the rows inside of that table and summarizes it and gives us the value that we see on the bottom left. That's it. Now, things get interesting when we start adding other values. In this case, I'm adding year and month. Unfortunately, the coloring is not great with this template. But let's say we use 2012 month 2. It's highlighted here, but you can't really see it really well. It's highlighted here. What happens is for this cell over here, 4,971, the data gets filtered and it only calculates these three rows from months, these 2 rows. From month 2, 2012, we only do sum of revenue for these 2 fields. That's what's happening under the covers. And again, this is the same filter context as I showed you before inside the pivot table. This all works thanks to relationships and the way that we process the data. We have this data accessible. Now, the real interesting part of DAX comes to that we can actually play with this. We can play with this filter context and we can tell the engine to not use the relationships and do it what we tell it to do. Oh, actually here, yeah, it shows you these 2. Oh my God. All right, let me just quickly change this. It's on the covers here. I can't change it. Okay. I'm just going to tell you what it says then. It says calculate sum of revenue, filtering the entire date table to true. It's super hard to read. But what happens is now, it's what we've told the engine to do is, okay, instead of following the relationships, just do what I tell you. And what I've just told you is ignore the filter that comes from the relationship. I just want all the rows of the date table to be used. So in this case, for every row, as you can see, it shows you the same as the grand total because we've told the engine to ignore the filters that are being applied. So we tell it, filter the entire date table where each row is true, which means every row in the table. And again, gives us the filter context. it overrides the filter context and allows us to do things with it. So same thing what I can do here, and again, sorry for the hard to read. What we can see here is calculate sum of revenue, filter the entire date table where the date is smaller or equal than the max date table date. Now things get interesting. So what we're going to get now is a running sum. So what I've told them to do is, okay, filter the entire, all rows in the date table where the date column is smaller or equal than the max of the date table date. The max date table date is what is getting determined from the filter context. So what it means is it does something like this. Now you can see it's running, it's adding values, running totals. The max date is getting the value from month year, but in the filter context, we're saying, okay, calculate the entire invoice table based on what I told you. Instead of using that one month, I want to have the running sum. And again, we can now start playing with this filter context and we can use it to our advantage. And again, this is just a short intro of what it can do. There's lots of full day sessions on just be able to understand this. I think Marco and Alberto spent like half a day on understanding filter context. I hope by showing you this, you get some idea of what filter context means and how you can use it to your advantage and how it's actually being created. It's being created by a pivot table and relationships. Those are the two that create the context that we're in. And then we can use to our advantage. So we can use DAX to express business logic. It is designed to use in-memory data. DAX uses the row and filter context based on created things that are created by the model. So I don't want to go into this much deeper. I just hope that I give you an idea of how DAX works, and under the covers it's using that filter context again to generate how it needs to calculate things. And then you as a modeler, as an author, can determine and change the way that filter context works. Now, finally, I want to spend some time on direct query. I know it's also Phil's favorite topic. And again, we talked about this before. A lot of people want to use direct query because the business users do not want to wait for the data to load. They need real-time data access. They want to leverage a single security model. Unfortunately, oftentimes they trust their data source to handle performant analytical query patterns, concurrency, and security. Oftentimes, data sources are not ready for the onslaught that Power BI generates on top of this data sources. It's starting to generate inner joins. It's like you have a nicely 6-norm database that you've created, that you've been using for many years. It is used for transactional data. And now all of a sudden Power BI with direct query comes on top and it starts to generate analytical query patterns that look very different than any query patterns that you've ever had before. And performance is now going to suck. It is important to recognize, okay, when I want to use direct query, I fully commit to using direct query and I understand what's going on. And I'm going to optimize the model, the database system, to be able to work with this data and to be able to get performance out of it. Now, luckily, before, and we'll talk more about this in a second, before we only had one big way. You can either do everything import or everything direct query. That has changed, and that has changed for the good. For example, the initial thing that we released is something called composite models. So it allows mixing of data. So a single direct query model can include multiple direct query sources or a mix of direct query and import data. So for example, you have something like this. Sales data comes from the SQL EDW. You can combine the information on data from an Excel spreadsheet, and the targets come from an Oracle database. And all of this you can bring together into a single Power BI experience, a single Power BI report. This is called composite models. And I'll show you more about this in a second. Because the biggest bang for buck here that you can also use aggregations for is aggregations. And again, what we used to have is this world where we only had direct query and import. Direct query was needed when you have very large models and not everything fit into memory. Or you wanted your data to be super fresh, just like it needs to be up to date all the time. But unfortunately, when you wanted to actually have performance, you had to go to import. That made it pretty hard to work with big models in a performant manner. So what we've done with aggregations is combine the two, where we now have a combination of the two, directory and import. So if you look at such a scenario like this used to be the world before, where I had either all tables in import or all tables in directory mode. With composite models, we started to make this possible. Some tables are in import mode and some tables are in directory mode. But unfortunately, this still has potential performance issues, because now when I want to look at sales, I always have to send a query to the underlying database system for everything that I do. Potentially, I want to have this faster, because 9 out of 10 times, we don't need to look at sales data by individual customer. We just want to see sales by geography over date by employees. That's it. So what we've done is we introduced something else called aggregations. And aggregations allows us to have an aggregation table, which is not the same amount of granularity as the sales data on top of the other data. So in this case, what we have the sales aggregation table that we've used to look at sales data by geography and date. But the customer, well, if we want to look at customer by date, then it's using directory. So what happens is when I generate a query like this, and again, we don't write these queries ourselves, it's what the engine does for us, Power BI does for us. But if I drag in year and city and ask for the sum of sales amount, look at the sales amount, we ask for amount from the sales table, but actually it's not getting it from the sales table, it's actually getting it from the sales aggregation table. It hits the in-memory cache. This allows us to make an aggregation table that has a fraction of the amount of data that the big table has with all the granularity, and give instant performance for our users. Because if I now ask for something like this, give me summarized columns by year and customer name, then, and again, I'm asking now for sum of sales by amount from the amount column from the sales table, it's now actually generating a directory query. The good thing here is your business user didn't know anything. He did not see the sales aggregation table, because in his mind, he was just dragging in amounts from the sales table. Okay, the aggregations table is hidden, out of sight. He doesn't even see it. Our engine is smart enough to be able to identify what's going on and give you the right values. So let's take a quick look at a quick demo. So again, here I have Power BI Desktop. What I can do in here is I go to fact online sales and I'm dragging in count rows, and it is pretty instant. It's not that big of a data set. It's only 12 million rows of data. But again, I can go in here, I can go into my date table, I can do fiscal year, I can do fiscal month, I can dive in a bit deeper. And again, it is pretty fast. And I can do average sales price. So again, it's an average over unit price. I can drag that in. I can do it by color. I can make it into a tree map. And again, it's all instantaneous. It's all pretty fast. But this will change as soon as I wanted to take a look into, okay, I actually want to drill through, I want to see the sales by customer. And you can see now it's spinning and it's running. It's still pretty fast, but it's not as fast. So what I did here is, in this simple model, I actually created an aggregation that looks like this. Let me zoom in a bit. That kind of looks like this. We have fact online sales table, we have an aggregations table, and we have tables around it. The aggregations table, even though it was 12 million rows, if I go to my aggregations table, it actually is only 500,000 rows. It's hard to see maybe in the bottom, but it's only 500,000 rows. If I actually look at the file, let's see if I can show you. Let's see. Here, my aggregations, my file is only 5 megabytes. That's it. Even in memory, it's very small. This is, again, because instead of using 12 million rows, which the count row actually told us, we only have loaded in 500,000 rows. And this is what aggregations allows you to do. I didn't notice anything different. When I look at this table, it actually thinks the data is coming from my fact online sales table. Well, in truth, it actually gets it from the aggregations table. And it's pretty easy to set up. So again, I can go in here, I can do manage aggregations. And now I can tell the engine, okay, where do I need to get data from? So if I do a sum on the discount amount from the fact online sales table, you can actually get it from a discount amount underscore sum field from aggregations table instead. So it's not actually going to go iterate over the entire fact table in direct query mode. No, it's actually going to get it from aggregations table. And that aggregations table is, go look in here, is loaded in import mode. Look here on the right, it says import. My fact online sales table is in direct query mode. My tables are in dual mode, which is even also an interesting mode. What dual mode allows us to do is it allows the engine to do the smart thing. For example, if I want to see my sales by customer and year, it was going to create an inner join by customer, fact online sales, and date, and it's going to send the data query to the engine and get back. All the values from the date table will also be retrieved from direct query, the underlying data source. But if I look into my aggregations table, I want to see my year, just what I showed you before, sales amount and year, it's actually getting it from import mode. So the date table is imported and in direct query mode, both at the same time. The engine will decide what it needs to use, because we do not want to have you join data that is from direct query and imported mode all at the same time, because that will cost performance. So the engine will figure it out, and actually it will force you to put the storage mode in dual if you want to have this aggregation table created. And again, I'm not going to go into lots of details. There are full hour-long sessions, and probably Phil can talk for days on aggregations and composite models. But this is kind of like a quick overview of what it does and what it allows you to do. And it's not just for terabyte-sized models. Actually, in scenarios, simple scenarios like this, it can save you performance, it can save you time, it can save you things to load into memory. The only thing you have to be considerate of is if you're actually going to go look at the individual details, it is going to cost some load on your SQL Server database. But it's not massive because, again, 95% of your queries are going to be answered by your aggregation. And I think with that, that is the end of what I had to tell you. And I think we're also out of time for about an hour. So let me know if you have any questions. Let me turn it back
First
on.
of all, Kasper, that was awesome. I really appreciate you taking the time to dial in and take us through the model. It's such a rich environment, and I think you did a really good job explaining that. But you can stick around just for a little bit for some questions.
Yeah, of course. Yep.
Cool. So, I mean, it doesn't have to be about anything directly on the session. It could be something about Kasper's work at Microsoft. So please feel free to make excellent use of this time.
Kasper, I've got a question for you, and it's just about calculation groups, which aren't in Power BI yet, right? But they're coming to Power BI.
Yep.
And also related to that compatibility level. And why I bring these two things up together is, will calculation groups ever get into Excel? I understand the Excel VerPack engine is on a different compatibility level than the Power BI one. Have I got the right terminology there?
Yeah, you got the right terminology. Yes.
So
the answer.
Will they update Power Pivot? Basically, is what I'm asking.
So I don't know. And the reason why I'm saying this is because Power Pivot is no longer my baby. It's from the Excel team owns it.
Yeah.
And actually, interestingly enough, they have the engine with that contains calculation groups, but they just haven't decided to turn it on.
Ah, okay.
So this is why we have the compatibility level, so that they can force the engine to run on a different compatibility level.
Yeah, Kasper, my understanding, I think fairly early on when it got built into Excel, it was quite tightly coupled, and I believe it's a very expensive operation to uncouple that, and I think there's a lot of people are keen to do it, but it's expensive and not cheap.
I think the biggest thing is because it's owned by the the reason why, and this is maybe a bit too much that I can actually share, but let me think about how I can say this. I think the biggest thing is Power Pivot is now owned by the Excel team because we couldn't innovate fast enough in Excel world. So the Excel team now owns it, and they have different priorities than updating getting all the new functionalities and features into Power Pivot. So I have no idea what they're actually thinking about doing with Power Pivot and what they're thinking about adding. I don't think calculation groups is going to come anytime soon. It is not that expensive, but I think their main concern is, first of all, one is because Excel has all these different users all over the world, and also it has all the how should I say it? It's really hard to update Excel. And the biggest problem that we saw when we started doing Power Pivot is that we were running behind because we did release Power Pivot, and then actually no one was upgrading because they were stuck behind IT that says, well, guys, sorry, we can't update Excel. And then they said, well, my Tableau here has all these amazing features. I said, well, we have these amazing features, you just have to update your Excel. Oh, updating your Excel, that's not possible in our organization. So this is one of the biggest reasons that we said, okay, like we're losing the battle here because people cannot upgrade their Excel fast enough. We have to move to a different product. And this is why we're doing Power BI Desktop, which can be updated independently of Excel. I'm not sure that's
I have another quick Excel-related question for you. This will be another interesting one for you, which is, why doesn't Power BI cache the state of visuals like Excel does? Let me explain that. So you've got a whole lot of graphs in Excel on page 1, tab 1. You click the tab 2, you click back to tab 1. No recalculation happens. It remembers what all those graphs look like. In Power BI, you've got a whole lot of graphs on page 1. You click on page 2, everything gets recalculated. It's a real pain. Why is that? What is the need?
I think it's not a need. I think it's just adding that is more cost. Okay. So maybe we'll add it at one point. Actually, this actually is possible now. When you update a Power BI file to the service, it actually does store the client cache as well. So there's now some more caching inside the Power BI service that actually, when you open up a Power BI report, it actually doesn't fetch all the queries again, even for bookmarks.
That's good to know, and I'll put an idea if it's not already one on community. It's just that it makes your really awesome product. It makes it look slow when you change pages, and it's a real shame because it's a really fast product unless you change pages.
Well, I think if it takes a long time for your page to load, then there is something else wrong as well. So you should take a look into why the pages get
aggregations.
You need aggregations.
Thank you.
I'm not sure, but yeah.
I think and feature last.
No, and I do want to say one thing about this question as well. Like, there is also a problem with being able to cache these things, because if you use direct query and if you use live connection to analysis services, or if you use live connection to data sets in Power BI, like, how do you know when the data has changed? If your data has been reprocessed in the engine, then you might get old results and old data. So it's kind of a slippery slope. I can imagine why they've decided to not do it. Let's put it this way.
Thank you.
Cool. Anyone else in the room? Not Jeff?
I have a question.
I have more questions.
Yeah. Jonathan.
Will composite models support live connection?
Yes, at one point. So there are people working on it. It's a major effort. So I have no timeline, but devs are actually coding. And if you think about it, it is very, very complicated. Because what you will then do is that you create a model on top of a model. So you create a model, just like you have today, but you create this model on top of an analysis services model. So what's going to happen with like measures and things like this? How's that really going to work? So that's why engineers are thinking hard on how to solve this.
Thank you.
It's a frequently asked for feature. There's a lot of people asking for it, and I think they can do good things. So we do know that it's an important thing to work on. So.
Yep.
I have another one, but my name is still Jeff. I'm going to ask it anyway. Is there any difference in the efficiency of implicit versus explicit measures?
No.
No. Okay. Great. Thank you.
That was quick.
Cool. Awesome. All right. Well, again, thank you very much for dialing in, Kasper. You can feel free to stop the record and sign all
All
up.
right.
We'll do the wrap ups, and I'll no doubt talk to you later in the week. So yeah.